It does kind of feel like a slow start to the day, at least for me. My computer is not behaving. It's throwing everything I open to like the back side of my screens. I hate when it does that. Instead of bringing it to the front, it's throwing it to the back of everything. God, it's annoying. I think I also need to restart my computer because I don't think I've done that for a couple weeks. But shh, don't tell Mr. Struess that because he'd be mad. All right, we have a tiny class today. We have a couple people who are at appointments or out sick today, so it's going to be a tiny class, but that's okay. We can get a lot accomplished with small classes here. With that being said, we are going to look at lesson 5 today, so 2.05. Yeah, it's that time of year, you know, the flu bug and colds are going around. So hopefully we can escape it for as long as possible. I have tea this morning to kind of help with the whole cold issue. We didn't get it like full blown in our house, but we definitely had it starting to make its rounds, so not good. All right. We are going to continue talking about those complex zeros. So we're looking at polynomials that have higher than degree 2. We started looking at how to solve those. Obviously, we did that in Algebra 2. We had the whole long format, all the steps laid out and explained in great detail. And here we're just kind of revamping those, revisiting and taking it up kind of another level, so to speak, with the complexity of the polynomials that we're looking at. So last week we just started reviewing all the different steps on how to solve those higher degree polynomials, and today we're going to continue with that. So we're going to take a look at what happens when we run into those complex zeros. Before I get started though, were there any questions with last week's work? So anything you want me to go over from the homework assignments that you're super stumped on? Anything from 2.03 or 2.04 that you want me to address before we look at 2.05 today? Okay, I see Rebecca is typing, so I'll let her finish that. The other thing I just want to mention is that it is a short week for us this week. This is the only live class that I'll see you guys in. You do have off Thursday and Friday, so enjoy your 4-day weekend. If you have any missing work in any of your classes, not just pre-calc, but any of your classes, Thursday and Friday would be a good time to catch up in those. So just keep in mind, 4-day weekend. I won't be available for help Thursday or Friday. I'm in meetings all day, but if you do need me, send me an email because that'll be the only way that I can respond Thursday, Friday. Yes, so if there's no constant in a cubic function, you can find the zeros by factoring. You would want to take out the GCF, which would be an x in that case. So what Rebecca is asking is if you're posed with a question like this, x cubed plus x squared plus x or something like that. So you got a cubic function, degree 3, no constant at the end. Can she solve that by factoring? Yes, you can. You take out the GCF of x. You see what's left over. What's left over is degree 2 now. I probably picked a bad example, but once you have that x taken out, you can try to factor the remains. Yep, most definitely. You can, even if there was a constant at the end, you could try factoring by grouping. It's not guaranteed to work all the time, but you could also try factoring by grouping if there was a constant at the end. So great question. Anything else before we get started today? Okay, then we're going to go ahead and take a look at these complex zeros. So just maybe a little bit new information along the way, but again, we're still kind of continuing with the process that we learned last week. So using synthetic division, trying to get down to a quadratic function at some point so that we can maybe try factoring or using the quadratic formula to help us solve for any remaining zeros. When we get to the quadratic function part though, we're probably going to have to rely on our quadratic formula a little bit more when we're dealing with complex zeros, because remember, complex zeros deal with imaginary numbers, right? So we're not necessarily going to see x-intercepts or see the graph cross the x-axis at a certain point. So complex numbers are those that have imaginary parts to it. So you'll have a real number and then plus or minus an imaginary part. Remember that these complex numbers always come in pairs. We actually call them conjugates of each other. So if you have a plus bi as a 0, you also know that a minus bi will be a 0 as well. And we'll talk more about those conjugates coming up. But just remember that complex numbers, they come in pairs when they are zeros. Okay. Hopefully these complex numbers are nothing new to you. We have seen them in the past all the way back to almost Algebra 1 when we learned that we can't have a negative number under a square root sign. Right? So instead of writing a negative number underneath the square root sign, we introduce the value of I to take that place. And that I becomes our imaginary number. The other thing I want to point out as we're trying to solve these higher degree polynomials, don't forget that fundamental theorem of algebra. So whatever the degree of the polynomial is how many zeros it has. So don't forget about that fundamental theorem of algebra there. Okay. The next part that they introduced in your ebook is, or your actual book I should say, not ebook. So used to previous years and we had ebooks instead of hardcover, but this year you got a hardcover. Yay! They talk about linear factorization. So the linear factorization is just writing your polynomial out as factors. So here are some examples of the factors and linear factorization. So notice how they don't actually distribute any of this to get the full polynomial, or maybe when they do have the full polynomial, they break it down to solve for x, but they express the answer as factors instead of x equals. So if you ever see that term linear factorization, this is what it's referring to. So all of the zeros expressed as factors multiplied together. Okay, so nothing too out of the ordinary there. It's just kind of knowing what that term refers to. All right, with example 1 though, it says to write the polynomial function in standard form and identify the zeros of the function and the x-intercepts of the graph. Now this is different because when it says identify zeros and x-intercepts, zeros are obviously, we always heard of where it crosses the x-axis, but now in our case, zeros also include your complex numbers. Right? X-intercepts are strictly where it crosses the x-axis. So you can have additional zeros now that don't necessarily cross your x-axis. So that's why they express them using two different terms. Does that make sense to everybody? So not every zero is going to cross our x-axis in these polynomials. The zeros that don't cross the x-axis are what we call those complex numbers. All right, so looking at part A, let's start by identifying what the zeros actually are going to be. So what are the zeros going to be there? Notice that they already have it set up in the linear factorization, so they found the factors for you. You just need to solve for x in each part. So what will x equal in each of the factors in part A? Let's start with that pink one. So if you have x minus 2i equals 0, what will x equal? A positive 2i, right? What about the second parentheses? And I'll highlight that in like a blue color. X plus 2i equals 0. If you were to solve for x there, you get a negative 2i. Now, we expect that, right? Because that 2i is a complex number. So if we have a complex number, its conjugate should also be a solution. All right, so those are the zeros. Are there any x-intercepts for that polynomial? So if those are the zeros, are there any x-intercepts to the graph? There are not, no, because we don't have x equals an integer value, right? So because we don't have x equaling an integer value of some sort, it's not going to cross the x-axis anywhere. All right, let's verify that by actually finding the polynomial here. So let's distribute and then combine like terms and see what the resulting polynomial is going to be. So I'll distribute the x first, so x times x squared, x times 2i is a 2xi. And can you guys hear the dog barking in the background? I apologize if you can. Okay, I'm so sorry. My husband threw her in and left, so now she's all has this anxiety going on. And then the last one, negative 2i times positive 2i. What is that going to be? Because I think we need to refresh this part for sure. What's negative 2i times positive 2i? And think of I as just a variable, right? So what is, oh, I see some big typing, so I'll wait a minute. A negative 4i squared. I like the negative 4i squared. We don't want to put the x in there because there's no x when we're multiplying, but I like the I squared piece of it. We can replace I squared. Does anybody remember what I squared equals that I can replace this with? So we're going way back in the files for this one. Negative 1. Yeah, so if we see an I squared as we start to distribute things, we're going to replace that with a negative 1. So instead of writing, I'll replace it here. Everybody's okay with me canceling out the middle terms, right? Everyone notices that those cancel? We'll get a negative 4 times a negative 1, which is an x squared plus 4. Because those middle terms drop out. We want the xi's and the I-axis to drop out along the way. If they don't, we made a mistake somewhere with our multiplication. So always go back and check. So if there's an xi term anywhere left in your polynomial, you made a mistake with multiplication somewhere along the line. So go back and try to find that. You should always have these cancel out in the middle. Now, if I wanted to bring up my graphing calculator real quickly here, and I'm going to type in y equals x squared plus 4, you'll notice that that is a parabola up here, but it does not cross the x-axis anywhere, right? So there are no x-intercepts, just like we predicted, but there are still 2 zeros because our degree is 2 on the polynomial. So those zeros are our complex numbers, and that would be your 2i and your negative 2i. questions with that first one at all? Okay, now we're not going to expand Part B fully because I'm running on a time already, believe it or not. The complex numbers are on the graph, yes, but not in a way you can see them because you need a third axis. So technically they are, but we would have to change from our XY coordinate plane to our real and an imaginary coordinate plane. So technically they are on the graph, but not in the same coordinate system that we're looking at. So we almost have to kind of switch to a different coordinate system to see that. So I guess the short answer there is yes and no. No, you're not going to see them on the XY coordinate plane. But yes, they technically are still there on a real and an imaginary coordinate plane. And we'll talk, I think we addressed that later on. I can't remember if we actually look at the real and imaginary axis in this one. Right? You can see why they're called complex, for sure. All right, looking at Part B, we're not going to do everything like I did with Part A, but we are going to hit upon some of the topics here. So first of all, how many zeros are there in Part B? There's 3, because you have 3 factors, right? So there are 3 zeros, which means that your polynomial, after you expand it, should be degree 3 of some sort. All right, let's find the 3 zeros for Part B. Let's start with the x minus 5. And I'll erase some of these black lines I had from Part A there, so it's easier to see. If I start with that first factor of x minus 5, what will x equal there? Positive 5, yep. Let's move to the middle factor, x minus the square root of 2i. What will x equal if I solve for that in the middle factor? Positive square root 2i. And the I is on the outside. It's kind of hard to see. It's on the outside there. We don't put I underneath the square root signs there. And then the last one, this is a complex number, right? So we expect its conjugate to also be a 0. So hopefully when we solve for x in the last one here, it's going to be the conjugate of that complex number. What do we get there for that last 0? Negative square root 2i. Gotta love the football. Okay, so we have the 3 zeros. Out of those 3 zeros, how many of those are x-intercepts? So out of the 3 zeros, how many x-intercepts are there? There is 1. What is the 1 x-intercept? 5, right? So technically you have 3 zeros, but your graph will only cross the x-axis once. And it's going to cross the x-axis at that positive 5. Good. You will not see the other 2 zeros on your graph, so you're not going to see it cross at the square root of 2 and negative square root 2. It doesn't work that way. But there's still zeros of that function. Questions with that idea at all? Okay. If you want to see that distributed, I think it's done in the book, I want to say. So just check out the book for example 1, and you can see how that is going to be distributed to get that actual polynomial. All right, if you are given the zeros, can you work backwards to actually find the polynomial then? So what they're doing is they're giving us the zeros. We got to take it a step back to write the linear factorization. Once we have the linear factorization, then we just distribute it all. Let's start with the zeros that they give us. They say that our polynomial has zeros of -3, 4, and 2 minus I. Now, anytime they give us zeros and we have a complex number, we have to make sure that its conjugate is also listed. Now I notice that they don't list the conjugate here, so they try to trick us a little bit. There is another 0 to this function. They just don't have it listed. What is the other 0 for the function? Two plus I, yeah. So notice how they have the 2 minus I. Well, right above there in the definition of complex conjugate, it says that they always come in pairs, right? So if you have a minus or a plus that is present, the other one must also occur. So the only thing that really changes is that operation sign that connects the two. So we know that 2 plus I is also a 0 to this polynomial. So that's the first thing I want you to be on the lookout for, are those complex numbers, and make sure they're coming in pairs. Because if they're not, you need to represent that second pair for that complex conjugate. All right, let's go ahead and take it a step backwards and find the linear factorization for this polynomial now. So let's start with x equaling -3. If x equals -3, what's the factor that I can represent that with? X plus 3, right? Because you have to add 3 to both sides. The next 0 they give us is x equals 4. What is that listed as a factor? X minus 4. The next one they give us is x equals 2 minus I. And this is going to have 3 terms now. So when I move the 2 over and when I move the minus I over, I'm going to have 3 things on one side. What am I going to have on the one side of the x now with that 0? You're going to subtract the 2, right? So it'll be a -2, but then you have to add the I. Yep. And then with the last one, x equals 2 plus I, how would I move that over to get my factor? What would my factor look like there? Yep, x minus 2 minus I. All right, now that we've got the linear factorization, we're going to go ahead and distribute to find the actual polynomial. So let's start with these right here. Those are probably the easier of the two, right? So we'll start with x times x, and I'll color coordinate this. X squared, -4x, +3x, -12, which when I combine like terms brings me down to an x squared minus x minus 12. Everyone good with distributing those first 2 parentheses? So hopefully you're good with that. That's all the way back to like our pre-algebra days, Algebra 1 days just about. All right, now the second set here, the second grouping, is a little bit more challenging. And I say that only because you're actually distributing 3 things versus just 2. So it's not really more challenging, it's just a little bit longer. So we'll start by distributing the x to everything. So doing that is going to give me an x squared, a minus 2x, and a minus xi. So is everyone good with distributing the x to the first, or to that parentheses? All right, let's distribute the -2 now. -2 times x, -2 times -2, and -2 times -I. Okay, that was a little bit weird, but any questions with the next set? So we're distributing that -2 through the parentheses. Okay, then the last thing we want to distribute is the positive I. So that would be a positive xi, a -2i, and a negative I squared. All right, any questions with the distributing there, with the three terms? So not really like complicated, but it is a little bit longer than we're used to because we had to distribute 3 times versus just the 2. Now the hard part is, well, I have an I squared, right? So the first thing I'm going to do is replace the I squared with the negative 1. So I'm going to take this last one, and instead of I squared, we'll put a negative 1 there. And if I substitute that with a negative 1, technically that's going to turn into a plus 1 at the very, very end. Is everyone okay if I change this to a plus 1 at the end? Because you have a negative, negative 1. Okay, so I'm going to erase that and put our plus 1 there. Let's look for like terms that we can combine now. So I see my x squared. And let's look for all the x's next. So I got a negative 2x, negative 2x. That's all I see. So what is that, a negative 4x? And then we'll look for the constants. Where are my constants? A 4 plus 1. Everything else should cancel out, right? Because we don't want any i's left in our polynomial. So everything else should cancel out, and let's just verify that it does. So I have a negative xi. I should have a positive xi to cancel that out. So that's gone. Good. I have a positive 2i and a negative 2i. Those are gone. So good. Every I that we had is now gone because it canceled out. All right, I am going to combine by adding these 2 polynomials together now, right? Or technically not adding, sorry, we have to multiply. Eeks. That scared me for a minute. All right, so we are going to distribute one more time and then combine terms one more time to get our final polynomial. So we'll start by distributing the x squared. And I'm going to move this over just a tad so they're closer together. X squared times x squared is x to the 4th, then minus 4x cubed plus 5x squared. Then we'll distribute the negative x. So that'll give us a negative x cubed, a positive 4x squared, and a negative 5x. And then lastly, we'll distribute the negative 12. That gives us a negative 12x squared, a positive 48x, and looks like a negative 60 at the end. Yikes. All right, combining terms one last time. I'm going to start with the x to the 4th because there's no other degree 4s there. Now I'm going to look for the x cubes because there should be at least one other one. Negative 4 minus 1 is a negative 5. Turn to the x squared. What does that simplify to? 5, 4 is 9. 9 minus 12 is a negative 3. The x's, what is negative 5 plus 48? Is that a positive 43? Check my math here because now I'm going, it's all mental. And it is early in the morning, so check for any addition errors there. I think that's going to be okay though. Whew. That took a while. Questions with how we got that resulting polynomial? All right, so these aren't necessarily extremely difficult, like process-wise, but they do take a long time. So just make sure, and anything that takes a long time, because there's a lot of steps, there's a chance for an error. So in most cases, if we don't get this correct polynomial, it's probably because we multiplied or added wrong somewhere along the way. So just make sure you're really careful with your multiplication and you're combining like terms. Okay, let's take a look at this polynomial, and it says find all zeros of the polynomial. Write your answer in as linear factorization. So what they do is if they just give you the polynomial, my suggestion for you is to always graph it first. Because if we can graph it, we more than likely can pick out the x-intercepts. Once we have the x-intercepts, we can use synthetic division to help us find any remaining zeros there might be. All right, so looking at the polynomial, first of all, how many zeros does this polynomial have? It's got 5, right? So we're looking for 5 factors to make up our answer. According to the graph there, we can probably pick out 3 of them. What are the 3 x-intercepts that we see? A -2, a +1, and a +4. All right, so let's start by using synthetic division to test those 3 zeros and make sure that, first of all, they are actually zeros. And second of all, if they are, it's going to help us get down to the resulting polynomial. And hopefully we can factor that or use your quadratic formula to solve. All right, so I'm going to set up -2 and then the nice long process. Now, as we go here, I'm going to just use our resulting polynomials to help us. So remember synthetic division, below the line multiply, above the line you add. So as I'm going through this, check for any mistakes. Now, instead of a 0, I'm going to put an X there because that means no remainder. So -2 worked out. The next thing I want to test is my +1. So I'm just going to use that resulting answer there and do synthetic division again with it. So below the line, we multiply. Above, we add. Yay, 1 was also a 0. So we're on a roll. The last one we want to test out is our +4. Hey, that worked out as well. Good. All right, so I'm left with the 101. So what is the resulting polynomial that goes along with 101? Remember, every time we do the synthetic division, we go down a degree. So this would be x to the 4th, x cubed, x squared, right? So we know that that's a 1x squared plus 0x plus 1, which is technically just your x squared plus 1. Okay, you could go ahead and actually use the quadratic formula to solve for x in this case, but because it's just an x squared plus a constant, it's going to be faster just to set it equal to 0 and solve. So let's come off to the side here a little bit. Take this x squared plus 1, set it equal to 0, and now solve for x. How would you solve for x there? You'd start by subtracting 1. Then what would you do? You take the square root of both sides. Now when you take the square root, it's a plus or minus. All right, what is the square root of -1? What can I replace that with? An I, yeah. So technically the last two zeros here, so all 5 zeros, if I were to write them up above, -2, 1, 4, you'd have a positive I and a negative I for the last two zeros. So there are all 5 zeros of that polynomial. Now it does say to write the linear factorization of that. So technically we would do an x plus 2, an x minus 1, an x minus 4, and believe it or not, we can actually write the last one using the x squared plus 1. If you wanted to do like an x minus I and an x plus I, you could, but an x squared plus 1 is also acceptable. So if you wanted, instead of writing this, you could break it down into an x minus I, x plus I. Those are the same two things, so you could do that. So this right here is the exact same as this x squared plus 1. Questions with how we solved for the resulting two zeros, so those complex zeros. I think that's going to be the hardest part of this lesson, is finding those complex zeros. All right, here, another example. It says the complex number z equals 1 minus 2i is a zero of that polynomial. Find the remaining zeros and write its linear factorization. They only give you 1 0 to begin with, but we're smart enough and we know that the zero they gave us is complex. So technically complex numbers come in pairs. What's the other zero that we know of that polynomial? 1 plus 2i. Yeah, so 1 minus 2i is a 0, and so is 1 plus 2i. All right. No, you could go ahead and graph and see if that crosses the x-axis anywhere, and hope that the other two zeros are going to be x-intercepts. But there's another way we can go about it. So algebraically, we're going to go ahead and write these two things as factors. So I'm going to say, well, that's x minus 1 plus 2i, and x minus 1 minus 2i. Is everyone okay with how I took those zeros and then created the factors for them? All right, then you'd want to distribute and combine like terms. Now, because we're running out of time, I want you to trust me. I've done this before or already. When I distribute and combine like terms, we will get a polynomial of x squared minus 2x plus 5. So later on, if you want to check that math and make sure that you can get that same polynomial, you can. But for time constraints, that's what we should get. All right, so what I'm going to do to find the resulting two zeros that are left, right, because there are 4 zeros total to this polynomial. We have 2 of them already. We need the other 2. So we're going to divide to find those. We're going to take the factor, x squared minus 2x plus 5, put that on the outside. Underneath, we're going to take our polynomial. We have to use long division here because the x squared minus 2x plus 5 is not linear. That's a parabola, right? So we've got to use long division. All right, hopefully this long division comes out with no remainder. That's the goal. So let's see. We can start this out with a 4x squared, it looks like. That's a negative. And I missed a 0 because now everything is kind of off. So let me put this up a tad. Okay. Notice how there wasn't an x cubed term. So as I got that x cubed, I noticed there was nothing to line it up with. So I'm going to put the missing term back in there with a 0 for a placeholder. All right, we're going to go through and do the opposites of all those because it is long division. Bring down the 14x. And then it starts over. X squared times what is 8x cubed? Is that going to be my 8x there? Yeah? Okay, so then we'll go ahead, multiply through again. And then take the opposite of those all. Because you want that first term to cancel out. I think that's going to be a 26x there. Last thing, x squared times what is 13x squared? A 13 is going to round us out here, hopefully. Take the opposites of those all, and we get 0 for our remainder. Yay! So here's the other resulting polynomial. From here, you would try to factor or use your quadratic formula to help you solve. Unfortunately, factoring does not work there. You do need to use your quadratic formula. For those that need the refresher with your quadratic formula, it's opposite b plus or minus the square root of b squared minus 4ac all over 2a. Remember that wonderful quadratic formula? Using substitution from this pink polynomial is actually going to give you another complex number. After you're done simplifying it all, it's going to turn out to a -1 plus or minus 3/2 I. So this polynomial, when you go to graph it, is actually not going to cross the x-axis at all. Because all of its zeros are complex. All right, so there are the 4 zeros to that polynomial. Not very pretty. Okay, any questions with that process at all? So it's a tedious process, that's for sure. Right? You're like, oh man. All right, don't forget, if you see multiplicity, that just means that 0 is represented that many times. So if you have a polynomial here with multiplicity 2, it means that 2 is listed twice. So x equals 2 and x equals 2. Right? So don't forget that's what multiplicity means. Real fast, we'll end today with how many complex and real zeros the function has. we will be graphing to test these out. So let's start, first of all, how many, in 21 here, how many zeros does that polynomial have? It's got 2. Out of those 2 zeros, I just went ahead and graphed it. How many of those are x-intercepts? 0. So what that means is there are 2 complex and 0 real solutions. So real solutions are your x-intercepts. All right, let's look at question 23. How many zeros are there total? There are 3 zeros total. Out of those 3 zeros, how many are complex? Yep, looking at the graph, 2 complex, which means there's 1 real, right? Because it crosses the axis at 1 spot. So that's your 1 real solution. Last one, how many zeros total? 4. I'm going to readjust our graph a bit to actually see the whole thing. We'll probably zoom out a tad just to make sure. All right, out of the 4, how many are complex? And how many are real? Yep, 2 of each. 2 complex, 2 real. 2 real because we see it cross the graph at 2 spots. And since there are 4 total, that means 2 of them have to be complex. Good. So you have to use your logic there by looking at how many x-intercepts there are and how many zeros total the polynomial has. So using your logic, you should be able to identify how many of those zeros are complex. Okay, a lot of stuff in lesson 5 here. I think we're in lesson 5. Yeah. Any questions with the process on how to go about finding the zeros and the complex zeros? All right, it's tedious. All right, we don't have another class this week, obviously, so I think 2.05 is the only lesson that you'll have to wrap up. We will start out next week with questions from 2.05. So if you run into any questions, make sure you bring them with you to next week, Tuesday's class. And we can start with those. All right, that's all I got for you this week, though. So enjoy your 4-day weekend, you guys, and I'll see you next week. Bye, everyone.